Welcome to VW 7.4. Today we're going to be talking about the last part of this chapter. So let's get right into it. Using the conjugate pairs theorem. So you're definitely going to want to highlight this. This is a huge theorem for this particular part of the book. The theorem says if a plus bi is a root of a polynomial function, then a minus bi is also a root. So essentially it's saying, for example, if 1 plus I is a root, 1 minus I is also a root. And you've actually seen this before in the quadratics unit, where we said if 2 plus root 3 is a root, then 2 minus root 3 is also a root. Just then we referred to it as conjugate pairs. Now we're going to have a formal theorem for it. So the question says, a function of degree 5, coefficients are real, has these zeros. Find the remaining 2 zeros. So essentially, if I were to write all the zeros here, we'd say 1, 5i, negative 5i, then 1 plus I, and 1 minus I. And we want to note that right here, right there is our conjugate pairs, our conjugate pair, and you have another conjugate pair right there. That's part one. Now we're going to use that idea to push this concept even further. The next example says find a function of degree 4 whose coefficients are real and it has these zeros. 1, so they put 1 twice, and then negative 4 plus I. So essentially it's saying the zeros are going to be 1, I'll just write 1 twice because they wrote it, and then negative 4 plus I, negative 4 minus I. Okay, so that's what we have so far. I'm going to show you 2 ways to do this. Method 1, this is like the standard book method. I call it x minus the root. Essentially, we're going to do this concept of taking x and just subtract the root. Because if the zeros are 1, that means x minus 1 is the factor. So let's write that twice, x minus 1, x minus 1. And then here's where it gets a little bit harder. The other roots are a little more complex. So you got to write x minus negative 4 plus I, then x minus negative 4 minus I, like that. And our goal now is to multiply all of this, which looks really hard. It's actually not too bad. The first two you can do in your head, x squared minus 2x plus 1. Now the next two is where it gets harder. What we're going to do first is distribute. So that would be x plus 4 minus I, and x plus 4 plus I. Now what we're going to do is a little trick. We're going to add in parentheses right here, because that fundamentally does not change the value, but it makes it easier to look at. Because now, look at this. You have some quantity that's matching, and then plus something minus something. So essentially, what we just did is we created a difference of 2 squares. So if I keep going, this will be x squared minus 2x plus 1. And if that's a difference of 2 squares, think of it as, like, I'll put it over here. A plus b times a minus b is a squared minus b squared. That's the same thing. That's going to be x plus 4 squared minus I squared. So notice how this whole crazy thing boiled down to that. So now I have x squared minus 2x plus 1 this part hopefully you can do in your head. That'd be x squared plus 8x plus 16 minus I squared. That's simply plus 1. So why don't we just combine that now? Let's make that plus 17. Now once you're here, now it's just algebra. We're going to multiply, and I'll show you how I do it. I take this first term, distribute, second, distribute, third, distribute, but I write it like this. So let's take the first one, x to the fourth, and then that'll be plus 8x cubed plus 17 x squared. Then my second term, when I multiply, I'm going to write that underneath each appropriate term. So negative 2x cubed, and then that's me minus 16x squared minus 34x. And the next one, take this one, distribute. That's going to be x squared plus 8x plus 17. Now we just add it all together, and notice how it's all really nicely lined up. So f of x must equal x to the fourth plus 6x cubed plus, this would be 2x squared minus 26x plus 17. And there's our final answer. This is the function that would create all of these zeros. So that's method one, pretty algebra intensive. There is a second method that some people like to use. And we've actually done this in class already. Reverse complete the square. So I'll kind of show you how it makes it a little bit easier. Some people use this. What they do is they use reverse complete the square to handle the conjugate pairs. So they take the conjugate pairs and they bring them over here. So negative 4 plus minus I. So we're going to reverse it. So x plus 4 equals plus or minus I. We square everything. So x squared plus 8x plus 16 is negative 1. So now we get this piece. You grab this piece, and this basically takes you straight to this step here. So the main thing to note is right here, this you can't be avoided. You can't avoid this part. This is just heavy algebra, you got to do that. But this part right here, you'll notice this creating the difference of two squares. This can be avoided by doing reverse complete the square if you prefer that. So that's a second method. Now here's our last example. Find a fourth degree polynomial with real coefficients. So here's our zeros, and they give you a point. So really highlight that. What this is doing is it tells you there's a stretch value. So right now that's not really relevant. We'll get to that at the end. For now, just note there's a stretch happening. The zeros here are negative 2, 2, I, and negative I. And I'm going to go with method 1 here, x minus the root. That seems to be the easier route since the zeros are pretty simple. So we'll write f of x is equal to x plus 2, x minus 2, x plus I, and x minus I. And the fact they give you a point means there's a stretch value, so I do have to put an A right there. We got to figure out what this is at the end. So let's keep going. F of x equals A. That's x squared minus 4. This would be x squared plus 1 after you multiply it. Remember to note that I squared is negative 1. And now we have f of x is equal to A. This would be x to the fourth minus 3x squared minus 4. Once we're at this point, we pretty much have everything. We just got to plug in our value here. So let's plug it in. Let's plug in negative 150 for the y. And then we don't know A. Let's plug in 3 for x. So that would be 81 minus 27 minus 4. So negative 150 is equal to A times 50. So a is negative 3. So now we plug it back in. F of x must have been negative 3x to the fourth plus 9x squared plus 12. And that is our complete function.